Welcome back, everybody. This is our seventh session in JEE mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this session, we have made 6 videos in this series, and all of those videos can be found on our YouTube channel's playlist section. We have also started similar series for NEET previous years, so if some of your friends are preparing for that, then you can guide them through those videos also. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you'd like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, I think we have completed up to question number 30 around something. So yes, it looks like we moved up to question number 33. Now let's move to question number 34. So let's slide it down. So an insulating thin rod of length L has a linear charge density given to it. The rod is rotating about axis passing through the origin and perpendicular to the rod. If the rod makes n rotation per second, the average magnetic moment of the rod is. So we have to find out average magnetic moment, and as here charge density is variable, so again we have to use method of integration. So let's suppose this is our rod. Suppose this is our rod, and what we do in this type of scenario, we choose a small element of this rod. Suppose we consider a small element of this rod that is of thickness dx, and this element, now this rod is rotated about axis passing through the origin and perpendicular to the rod. So it is nowhere mentioned that the axis is passing through the center of the rod. It is passing through the axis of the rod and from the origin. And normally when it is given that rod has a length L and center is at origin, so then we assume that center is at the one end of the rod. So there is the rotation center. So we have considered element dx at distance x from the rod. So to find the magnetic moment, what we need, we have a formula for magnetic moment, that is Ni into A. So we need number of turns, or here it will be number of rotations. I is the current, and current we can find out using the after calculating the charge, and A is the area of that circle. So in this, first we have been given linear charge density, so we can say dq, or charge on this small element dx, will be rho node into x by L into dx. That will be the amount of charge on this small element. As this is linear charge density, so it is charge by length. We can write this rho x. This is given to be rho node x by L. Here this x is the distance from the center, and L is the original or we can say total length, and this will be total charge by the length of the element which we are considering here. So it will be something like this, and from this qx will be rho node x by L into dx. That's how we get this formula here. So we have the charge density. Now what we can do, we can make current out of it. So current flowing in the small element, that will be di. Di will be, as we have n number of rotations, as mentioned in the question, that rod is making n rotation per second. So this charge is being rotated n times per second, and current is total charge flowing in a 1 second. So total charge in 1 second, that will be n times the charge in one rotation, that is this, divided by 1, because in current we take calculation for 1 second. So from this di will be n rho node x by L into dx. This is the amount of charge. Now from this we can calculate the value of magnetic dipole moment for this small element. So that will be dm, we can say, as we have already included the number of turns here in the charge, so we have no need to include it in the formula of the magnetic dipole. So now formula for magnetic dipole will be just area times the current. So now area, it is the area that is the circumscribed by this small element dx. Here let me show you how we will calculate the area. This is our original element, and let's paste it here. So now when it rotates, now this small element will rotate, so it will circumscribe a circle like this. Let me adjust its thickness. So when this small element will rotate along the axis, then it will rotate in this circular form. And when this rotate in this circular form, while calculating the magnetic dipole moment, we take all the area inside that element. So here we don't have to take that area of this white element, we have to take all the area inside this white element circle. So means area of this circle, that will be pi x square. So dm will become, area will be pi x square into di, that is n rho node x L into dx. So it will be pi n rho node x cube divided by L into dx. This is the value of dm, and we can integrate it from limits 0 to the length of the rod, that is capital L. So it will be pi n rho node by L x cube integration dx will be x4 by 4, and putting limits it will be L4 by 4. So it get cancelled, and we will have a result pi n rho node L cube by 4, and if we match it, then it matches perfectly with option C. Now let's move to the next question. A coil of cross-section area A having n turns is placed in uniform magnetic field B. When it is rotated with angular velocity omega, the maximum EMF of the coil we have to find out. So again, as this coil is getting rotated with angular velocity omega, so its area with respect to the magnetic field will be changing, or we can say the flux. In this case, flux will be B A cos of omega t. Now this is the flux. We can find out the induced EMF. Induced EMF will be minus d phi by dt. So it will be B A omega, and it has n terms. Okay, so area will be n times, so we will have n additional here, so it will be n B A omega. Derivative of cos will be minus sign, minus will be positive, sine omega t. So maximum value of EMF will be when this sine omega t is equal to its maximum value, that is 1. So maximum induced EMF, that will be nba omega. And if we have to find out the minimum value, then in that case sine omega t will be 0 and minimum value of EMF will be by of course 0. So we have been asked maximum value here, so NBA omega will be the right answer here. Let's move to next one. An ideal capacitor of capacitance 0.2 microfarad is charged to a potential difference of 10 volts. The charging battery is then disconnected. The capacitor is then connected to ideal inductor of self-inductance 0.5 millihenry. The current at the time when potential difference across the capacitor is 5 volts. So here we have two cases. Initially we are charging a capacitor, and as we are charging a capacitor means it will store some energy. So initially energy of the capacitor will be half C V square, where C is this and value of potential difference is 10. Now when it is connected to an inductor of this value, then there will be exchange of current, means our final circuit will look like something like this, that we have a capacitor here. Initially it was connected to a battery, so it was charging, and after that this battery disconnected and we have an inductor here. So when we have an inductor, so our capacitor will start discharging and there will be some current flowing in the circuit, and potential drop across potential will keep on decreasing. So again we know that as assuming that wires are ideal and there is no loss of energy due to, we can say, heat or resistance, so total energy in both of these systems will stay constant or equal. So in this system total energy stored on capacitor is half CV square, and in this system total energy on capacitor is half CV dash square, that is the final potential, plus half in inductor the energy stored is half Li square. So half get cancelled. From this we can write that C into V square minus V dash square is equal to Li square. Now value of capacitor is, we have 0.2 microfarad, so 0.2 into 10 raised to power minus 6. Initial potential is 10, so 10 square 100, minus final potential is 5, so 5 square 25 is equal to L, that is 0.5 millihenry, or we can say 5 into 10 raised to power minus 4 into I square. So this will cancel at in 10 raised to power minus 2. So we will have 2 into 10 raised to power minus 2 into 75 divided by 10 and 5 from here. So this will on 5, 15 and 3. So it will be 3 into 10 raised to power minus 2 is equal to I, and that is I square actually. So I will be under root 3 into 10 raised to power minus 1. That will be 1.73 into 10 raised to power minus 1, or 1.73. Oh, sorry, 1.73 10 raised to power minus 1, or 0.173 ampere. That is option A. Now let's move to the next question. A copper rod of mass m slides under gravity on the two smooth parallel rails. So this is our rail that is coming down, and separation L, separation is L, no, this is not 1, it is L, and the set at angle theta with the horizontal. At the bottom rails are joined by a resistance R. There is uniform magnetic field normal to the plane of the rail. So the magnetic field is normal to the plane of the rail. So magnetic field is something like this, or we can say the magnetic field be magnetic field will be like this, and if we calculate the angles, this is theta and this is 90, so this is 90 plus theta, so it will be 180 minus 90 minus theta, or 90 minus theta. So this angle is 90 minus theta of the magnetic field with the horizontal line. The terminal speed of the rod of the copper. There is uniform field in the plane of paper. The terminal speed of the copper rod is. So what do we mean by here terminal speed? So terminal speed is the maximum speed that this copper rod can attain, and at maximum speed we can say we have one thing, that is acceleration at terminal speed. Acceleration will be 0, or we can say net force on the rod will be 0. And to find out the net force, we need to find out the components, that what will be the different force component and different forces acting on this rod. So on this rod, first of all we can say that there will be mass that will be acting downward. So mg will be acting downward for this rod. And this angle will be theta. So horizontal, this component will be mg cos theta, and there will be a component like this will be mg sin theta. This is mg cos theta, and there will be a component like this mg sin theta. Now coming to the magnetic force. So here I made a slight mistake, that while reading statement it is mentioned that magnetic field is normal to the plane of the rails. So magnetic field here is not in the parallel to this length, it is perpendicular to this length, so it is coming outward. So let me correct that. This is deleted, and magnetic field will be something here like this, out of the plane of the paper. So what we can do, normally we take our axis like this. We take our axis, this is suppose y axis, this is suppose x axis, and this is suppose z axis. If we rotate our x and y axis by some angle theta, then they will look like something this. Our y axis will be something slightly rotated. This is y axis, x axis slightly rotated, and z axis will stay the same as we are rotating about z axis. So here magnetic field is about z axis. Our velocity is in the negative x axis, and the length is in positive y axis. Means there will be a induced EMF, as all of these three are perpendicular, and induced EMF will be, we can say it will be BLV. Now this is the amount of induced EMF, and due to induced EMF there will be a current. That current is given by BLV by R, and as there is some current flowing through the conductor in a magnetic field, then there will be force acting on the conductor. That force will be that force formula is given by I into L cross B, and L and B here are perpendicular. Length is in the y axis and magnetic field is in the z axis, so they are perpendicular. Value of current is this, so force acting will be B square L square V divided by R. This is the amount of force acting on this conductor, and this force act in such a way that it opposes the motion of the conductor. As motion is coming in the downward direction or in the negative x direction in our rotated coordinate, so force will act such that it opposes this motion. So force or magnetic force will be acting in the opposite direction here. So this magnetic force, as per our condition, initial condition, that at terminal speed, acceleration should be 0. So this magnetic force should cancel out or should balance out this mg sine theta component. Or from this we can say b square L square V divided by R should equal to mg sine theta, and from this V will be mgr sine theta divided by b square L square, and that is option B for us. In this type of questions, what we can do, if we just rotate our coordinate system slightly, then they becomes quite easy to solve. Else what we have to do, we have to take a cross product after resolving length into its xy component in the normal xy, and then velocity also has to be resolved, and then we will take their cross component, and then we will find the force. That will be we can say more mathematically and time consuming process. To avoid this, what we can do, we can simply rotate our axis slightly so that our directions becomes aligned with our coordinate axis, and then we can solve it easily. Now moving to the next one. At the center of a fixed large circular coil of radius r, a much smaller coil of radius r, small r, is placed. Two coils are concentric, are in the same plane. Larger coil carries current I, smaller coil is set to rotate with constant angular velocity omega about its axis along their common diameter. So calculate the EMF induced in the smaller coil after time t of its start of rotation. So first of all, let's slide it in the left side. Now we have two coils. Suppose this is bigger coil of radius capital R, and this is smaller coil of radius small r. They are concentric. Its radius is small r and its radius is capital R. They are concentric, and the middle one is rotating with angular velocity omega. So as we have to find the induced EMF, so what we have to do, first we have to find out the amount of flux associated with the middle one, and then we can take a derivative of it to find out the amount of EMF induced. As current in the bigger one is I, current in the bigger one is I, so magnetic field at the center of the bigger one, suppose center is O, so magnetic field at the center will be mu node I by twice of the I. And here we will assume one condition, that the radius of this smaller ring is very small as compared to the radius of the bigger ring. Why this assumption? Because we have the formula for the center, we have the formula for the magnetic field at the center, but we don't have the formula for magnetic field elsewhere from the center. Or we can say, suppose if I choose a point A here inside the bigger ring, and if I am asked to find out the magnetic field here, then I don't have a definite formula for this for this point to find out the magnetic field at this point. I have only formula for finding magnetic field at the center. And as when we calculate the flux, then flux is calculated by taking the average value of magnetic field inside this coil multiplying the area of this coil. And as we don't have the formula for magnetic field at point A, what we assume here, that this coil, this central coil is very small as compared to the bigger coil. So the field inside it due to this bigger coil is almost constant and almost equal at each point inside this smaller coil. So that is our assumption. So with this assumption, we can calculate flux. Flux through smaller coil will be magnetic field at smaller coil, that is mu node I by twice of the R, multiplying the area of the smaller coil, that will be pi r square. And as already mentioned, that this smaller coil is rotating. Smaller coil is rotating with angular velocity omega. So here area is changing with respect to time. So we have to add cos omega t component also, as area vector is rotating with respect to time. So this is the flux. Now EMF induced will be negative of this d phi by dt. So this will be mu node I by 2 r into pi r square. Differentiation of cos omega t will be negative. We have already a negative sign here. Negative of sine omega t into omega t differentiation is omega. So this will be negative negative plus. We will have mu node I into omega pi r square divided by twice of r into sine of omega t, and that matches with option C of our question. So with this I end this video here. Hopefully what we have covered till now is helpful to you. Again, if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. And if you find this video useful, helpful, then do press the like button, share it as much as possible, and subscribe to my channel. And again, thanks for watching. We will meet in next video.